Hi everyone. So thanks you for having me to present here. So I will present you my latest work during my PhD in NTNU. Here are my supervisors, Zhang, Jianying and Shulu. So here we will be interested in the relation between fracture toughness and hydrogen. Um, okay. So I will try to make it straight to the point and give a clear message. So the outline will be a quick introduction of the model for hydrogen embrittlement prediction. Then some results on fracture toughness. So we worked on with a sand specimen and some takeaway messages. So let's get started. So when talk about void-based model, so we actually make the hypothesis that in every metal there are initial voids. So that's why we talk about porous material. So the main ideas are that the void, of course, nucleate with strain, but also they grow. At some point, there will be coalescence, so the void will reach each other, and that will lead to failure. That's what we call localized deformation. So those are the main ideas: nucleation, growth, until you reach coalescence of the voids. So here, this is a typical case of hydrogen embrittlement on a tensile test. So the maximum range of ductility is reached in air, of course. And as we know, the more we had hydrogen, the less ductility until we reach a critical hydrogen level in which the failure becomes brittle. So in a nutshell, the model is a G-chain-based model that has been improved. So the ductile fracture is predicted with the Thomason criterion. So we have a hydrogen diffusion model and trapping in Abacus using subroutines. We try to account for HELP and ESIF using an assisted void nucleation. And we have incorporated the brittle fracture mode, so HEDA. So the main idea and many research have been focusing recently on basically unifying both ductile fracture, but also the cohesion fracture in one model. So yeah, just to keep in mind, so basically in this model, there is a competition between ductile and brittle fracture. So here I will not go into details, but we have in here the ductile criterion. So of course, hydrogen will decrease the strain at failure. And here we have a decohesion. So as we can see in air, for example, here, the decohesion will never be reached. There will not be brittle fracture. But with enough hydrogen, the brittle fracture criterion will be reached and will be reached before the ductile one. So let's get some results. The two questions I want to answer for you today is how constraint and hydrogen concentration influence the fracture toughness first, but also the fracture mode. And then I want to show you how our model is capable to adapt to a given material you would be interested in, for example. So the main concept, so here if we focus on the blue curve in air, so this is the fracture toughness against a crack-tip constraint. This is a sand specimen. So I use a 2D plane strain simulation with one initial crack, length is A. The specimen width is W. So usually in the industry, we're interested into the fracture toughness for example, a pipe with an initial given small crack. So we want our simulations and tests, of course, to be conservative. So we want to be in this side of the curve with our test so that we actually predict a lower fracture toughness for security, you know? So here it will be the sand, for example. The question is how is this curve evolving with hydrogen? Because so here we have three hypotheses of evolution. So let's say with hydrogen, the curve could be following the same trend, but with just a reduced fracture toughness. We could imagine that hydrogen will neutralize the effect of the crack tip constraint. Or in a problematic case, we could imagine that the constraint with higher constraints, the fracture toughness would be more increased. And then we would have something non-conservative, and we would have some tests given a higher fracture toughness than the real case. That would be a problem. So this is the main question we try to tackle. So this is a complicated plot, but this is the main plot for this presentation. So we will take some time to understand it together. So if you look at the blue curve here, this is the curve in air. So I use the CTOD, so the crack tip opening to measure the fracture toughness. And for different constraints, I used different head over W. So I used different initial crack length. So the longer the crack length, the more constraint. Okay. So the blue curve follow the case in air. So that's already a good news for our results. Now, as we add hydrogen, we see those different curves with different initial hydrogen in the lattice. So the more we add hydrogen, the lower the curve. So this is an expected result. The fracture toughness decreases with hydrogen. So here we can already state that our model will follow the trend number 1, and the result will stay conservative, which is actually good news. The other idea in this plot, here I used so this represents crack initiation, so the start of the propagation of the crack. So the star shows the brittle, the ductile initiation, while the triangle shows a brittle initiation. So of course, in air, if you look at the blue curve, there will be only stars. In air, the behavior will be only ductile. And the more you add hydrogen, the more you go down, the more you will encounter triangles. So with the more hydrogen, you will encounter more brittleness. But what is very interesting also to observe is in here. So for example, with a very high constraint, with a long initial crack, you will reach a brittle initiation quite early with a quite low hydrogen level. If we go on the opposite side, for a low constraint, you will reach this critical hydrogen level later. You will need more hydrogen in this stress distribution to reach brittle fracture. And the transition from ductile to brittle is quite important because, as you can see, for each specimen, so here every time it's different specimen. So for one given specimen, the loss in fracture toughness is quite important when you transition from ductile to brittle. So every time you see, for example, here we have quite big losses. So that's why the understanding of the transition from ductile to brittle is quite important, actually. So here, this is just a demonstration of how we can adapt to one given material. So here I used a different assisted nucleation with hydrogen. So here we see the effects on the nucleation on the fracture on the fracture toughness against the hydrogen. So of course, when you're in air, the hydrogen enhanced nucleation has no effect, and the more you had hydrogen, the more the hydrogen will of course create a void. The red dot line shows the transition from ductile to brittle. So of course, when you reach such high hydrogen level, the void nucleation doesn't have much effect afterwards because the brittleness is predominant. So here there's the opposite. So here we keep the same hydrogen-assisted nucleation, but here we play with the decohesion. So we can, in our model, decide more or less for which hydrogen level will the material become brittle. So here we have different dashed line for different transition from ductile to brittle. The red curve would be the curve when it never becomes brittle. So yeah, this is just to show you how we can play with those curves with our two parameters. So for each behavior, we have one parameters. Okay, now I will go to my take-home messages. So the first idea is that with our model, we are able to capture the loss of ductility and then the transition from ductile to brittle. So we used assisted nucleation to take into account essive and health mechanisms and brittle criterion to account for head. The second idea is that, and the good news is that our model predicts that the fracture toughness curve will follow the same trend as in air, mirroring behavior in air. So this is a very important point here. However, of course, our model follow many hypotheses. And we have had some information coming from the industry that, for example, in the creep, when you have a constant load, they may have observed the H3 trend, which make us want to go further in the study, and in particularly with creep. So there is an urgent need to reveal the underlying mechanisms of the H3 scenario. Yeah, so that's for further study. And this is all for me. Thanks a lot for listening and paying attention. Yeah, sorry, I like to thank my project, Life Project, that has been financed by most of the oil and gas industries in Norway. So thanks for them.